ఒకసారి మ్యూట్ చేసుకోండి మీ మైక్. Okay, so good morning all. Yesterday I started the subject, that means just introduction. I introduced the subject power system analysis for you people. We have discussed the learning outcomes. So finally, what is the outcome of this particular subject once the course has been completed? Now in this particular case, course is nothing but your subject. So what the student is going to achieve after upon completion of this particular subject, power system analysis. Once again, not in brief, just we are rewinding the concepts what we have discussed in the last class. So this power system analysis is very, very important for analyzing the amount of voltages, real power, reactive powers at the various buses in the power system. Okay, so in the power systems we are having n number of buses. Okay, so n is varying, that is not fixed. So it is not equal to 1 or not equal to 2 or not equal to 3, etc. So it is a varying parameter. So n is defined from 1 2 3 and up to n number of buses. So in order to determine the amount of power that is flowing from a particular bus, or in order to find out the voltage, or in order to find out the phase angle at a particular bus, definitely we must have the information regarding the analysis of the power system. Okay, so for that purpose, the first chapter discusses about the per unit quantities representation, and we have already discussed about the advantages of per unit quantities. Why do we require per unit quantity of a particular equipment or a component? What happens if the various components that are used in our power systems contains different specifications? Specifications is nothing but the voltage, different voltage levels. So obviously we know we are having so many equipments that are connected in our power system. If that equipment is having different specifications, in that particular case it is not possible to analyze, okay, the required parameters at a particular node or a bus. So that's why we need a common reference value, that is called base value, and from that base value we can obtain the per unit value. So if we express all the values in a same platform, or by considering the common reference value, we can easily analyze that system. And this analysis is carried out by using the next chapter, that is power flow or load flow analysis. Particularly when we talk about the power flow analysis or load flow analysis, obviously we are having real powers and reactive power. So it is very, very important to have the real power and reactive power at a given bus. Why? Because in our power systems actually we are also having that there is a strong relationship between the power and load angle or phase angle. Okay, similarly reactive power and voltage. So once if we know the parameters of P and Q, obviously we are also able to determine V and delta. So similarly in this case, power flow analysis or load flow analysis, we are making the analysis based on the load voltages or generator voltage, generator real power, reactive power, etc., etc. We are mainly concentrating on real power, reactive power, voltage and phase angle at a given bus. So in order to determine these values at a specific bus, we are going to have four methods, that is Gauss-Seidel method, NR method, decoupled and fast decoupled methods. So these are the methods that are available for determining these parameters. These are electrical parameters, right? The third chapter is completely jet bus formation. Jet bus formation. So I told you the importance of jet bus formation also. So jet bus formation is particularly why we need to talk about the jet bus. Bus admittance, bus impedance, both are important, very, very important. Okay, so jet bus is nothing but the bus impedance. So why do we need to study about the bus impedance or some impedance in a power system? Why? Because whenever a fault occurs in a power system, the most affected parameter and the first and foremost factor that is going to be affected is only the impedance. If the impedance has been decreased, means obviously the current is trying to increased. So always there is a inverse relationship between both the factors. And after that we are going to have the fault analysis. So again, fault analysis is classified into two types: symmetrical fault analysis and unsymmetrical fault analysis. And obviously, we know that when a power system is said to be balanced, so the analysis becomes very easy. If the power system is said to be unbalanced, means obviously the power system analysis is quite difficult. Okay, it is not that much easy when we compare with the power, symmetrical. When the power system is balanced. So in our power systems, again you are having two states: balanced state, unbalanced state. Okay, so balanced state is completely different from unbalanced state. In a balanced power system, all the voltages, currents, phase angles, etc., all are equal in each and every phase. But that is not in the case of unbalanced. First of all, you people have to understand the clear difference between balanced power system and unbalanced power system. So once if you know or if you understand the concept of balanced and unbalanced systems, obviously you can easily analyze the power system behavior when it is exposed to a particular fault. That fault may be the three-phase fault, or it may be three-phase faults or comes under symmetrical faults, or it may be either line to ground faults or line to line fault or line to ground faults. So whatever it may be. Okay. And at last, we are having the stability concepts. Now we are going to determine the stability of a power system. So in that stability, we are using critical clearing angle, equal area criterion, and how do we improve the transient stability, etc., etc. Okay, so once again, I am talking, I'm saying that this subject is very easy to understand. So once if you focus on the classes, what I'm going to explain in the classroom teaching or online as well as offline, obviously this subject becomes very easy, one of the easiest subject in your semester, in this particular semester, right? So please don't take this subject as light. Okay, now we are going to start the first chapter, that is per unit representation and its topology. Okay, so now I'm going to share my screen here. You just go through this. See, most of the times there are power fluctuations in our college, so please try to understand the situation. So once if I went outside, obviously we will continue the class in the next class. That means tomorrow or day after tomorrow. Whenever we are having the class, obviously we shall continue, right? Please try to join before 5 minutes of the commencement of the class, right? Now I'm going to share my screen here. I think it is visible now. Right. So the per unit representation, please be very careful. Please try to concentrate on the lecture. Why? Because this per unit concepts is important throughout this subject, Okay. So once if you are having the knowledge regarding this per unit representations, obviously you can use the same analysis for the remaining chapters also. Okay. So from the second chapter onwards, directly I will use 1.1 PU. So per unit representation is always represented with the PU. Okay. Don't worry. I will clarify each and everything. Right. So first one is per unit representation. Right. The first concept is single line diagram. Single line diagram of a power system. So what do you mean by single line diagram? The first question is how to draw a single line diagram, and when it is possible to draw a single line diagram for the given power system. These are the two important questions you need to keep in your mind. Okay, so for balanced system and unbalanced, see, already we have discussed that systems are classified into two categories. The first one is balanced power system, second one is unbalanced power system. If the system is said to be balanced, then only it is possible to draw a single line diagram. Why? Because in order to make the analysis simple, we are considering only one phase and neutral. Suppose if the system is said to be balanced, means obviously we are going to consider that one phase and neutral. That is enough. And later, if we want to extend that analysis for three phase, you just multiply it by 3. This is only for balanced power systems, but that is not in the case of unbalanced power systems. So always we are trying to draw a single line diagram for balanced power systems. Balanced power systems. So what is a single line diagram? It is just nothing but a diagrammatic representation of the overall power system. Single line diagram means only you will have only one phase and neutral. Okay, you don't have any three phases. You need not represent the three phases, three reactors which are connected in three phases, so three circuit breakers, etc., etc., etc. System becomes bulky. So in order to simplify that one, we are considering a single line diagram. So single line diagram is a diagrammatic representation of a three phase balanced power system. Three phase balanced power systems, and we are considering single phase neutral for making the analysis of that particular power system. This is valid only for single line diagram is completely applicable to balanced power systems. Okay, so yeah, I'm not going to say that single line diagram is not possible for the unbalanced power system. If you want, you can draw, but what is the main function, what is the main thing we are going to learn in the single line diagram is we are using single line diagram for making the analysis of balanced power systems. Once if you obtain the voltage or current or power for the single line, you can extend that to the same analysis for the three phase also. Just you multiply it by 3. Suppose if I get I is equal to 2 amperes in R phase, then what about Y and what about B? R, Y, B phases, 3 phases, right? So if we get I is equal to 2 amperes in R phase, again in Y phase also you are getting 2, and B phase also you are also getting 2. Why? Because this is a balanced power system. So you need not do the analysis for the remaining two phases, Y phase and B phase. You just restrict your analysis for the single phase, that is R phase and neutral. If you get I is equal to 2 means obviously later you multiply that with 3, you will get a 3 phase current, right? So say total 6 amperes is the total current that is flowing in a 3 phase balanced power system. So the first point is a balanced power system is always analyzed on a per phase basis. Okay, so whenever we are saying that a system is said to be balanced means obviously we are using the per phase values, not line to line voltages or not line to line currents. We are talking about always we are talking about the per phase values, per phase voltage, per phase current, etc. Right? Now next point is, so it is enough to represent single phase and neutral in a diagrammatic representation which is called as a single line or one line diagram. Okay, so this is also very important. Sometimes directly you are getting a question that explain the following terms: single line diagram, reactance diagram, per unit impedance diagram. Okay, you will have three types of diagrams here. You need to explain each and every diagram by considering a single example. Later we will study about the remaining two types of diagrams also, but in this case, in this today's hour or today's topic is we are concentrating on single line diagram. So single line diagram is also called as one line diagram, right? So one line diagram. So it is a diagrammatic representation of a total three phase system, three phase power system, which is balanced by considering one phase and neutral. Right? Now, the third one is in single line diagram, all the power system components are replaced with the standard symbols and the transmission lines are represented with the straight lines. Okay. So, in the first 2 points, we are very clear that single line diagram is nothing but the diagrammatic representation of a total three phase balanced power system. Okay. And it is also uh, we are also coming to a conclusion that okay, single line diagram is a diagrammatic representation which is consisting of one phase and neutral, one phase and neutral. Now, how can we draw the single line diagram? That is also very important. Okay, just we have learned the definition. What is a single line diagram or what is a one line diagram? After learning the definition, how can we draw the single line diagram or one line diagram? That is also very important. Now, the third one is that is the thing. So, even though that is a single line diagram, definitely it must consist of the number of generators. So, you will have generators, transformers, buses, transmission lines, motor section, load section, etc. So in each and every power system, these are the common components that have been connected in the power system. Maybe that system is a balanced or unbalanced, we don't bother. But as far as the single line diagram is concerned, we are going to replace all the components of a power system, nothing but generator, transformer. I will show you the example also, don't worry about that. generators, transformers, transmission lines, etc. with the standard symbols. We are using standard symbols for representing all these components. And similarly, the transmission lines are represented with the straight lines, right? The next one is, next slide. Just wait a moment. Right. So I think we have seen this example. So in the yesterday's class, to explain the concept of per unit, that means per unit representation, I have explained, or I have taken the same example, okay, just to demonstrate how the components have been connected in a single line diagram and how the specifications of each and every component have been given. Now you see here, this is a single line, three phase balanced power system. This is a single line diagram. Single line diagram of a three phase balanced power system. So as far as the section 1, so see here, I will divide this total power system into number of sections. You just wait a moment. Right. Now see here. So this is section 1. Section 1. So I can say this is section 1. Okay. Now this is section 2. So this is section 3. Section 4. This is section 5. So for your understanding, I have divided the total power system, okay, the total single line diagram into 5 sections. Section 1 contains the generators. Okay, so always whatever it may be, whether it is a generator or motor, you are going to represent that with a circle by mentioning either G1, or suppose if it is a motor means now mention M. So we can conclude that. So these are the standard symbols for representing generator as well as motor. Always the circuit breakers are represented with the, see here, this is circuit breaker CB. CB, just a square box, that's enough. Now the transformers representation is this one, transformers. Now the load representation is always the static loads are represented with a line, arrow. So whenever we are representing this arrow means obviously that is a load. Okay. So in section 1, you will have 2 generators have been connected, and you will also have load which has been connected in section 1. Now see here the ratings of the 2 generators and the see here. So the generator connection is, it is a star connected, and the neutral point is grounded through a reactance. So this is neutral grounded reactance. Okay. So this is neutral grounded reactance. So similarly, the connection diagram or the connection of second unit is also exactly similar to that of the first one. So in the section 1, you will have 2 generators. So generator 1 is having a rating, or the power rating of generator 1 is 200 MVA, and the power rating of generator 2 is 10 MVA. The base voltage that we are operating this generator 1 and generator 2 is equal to 6.6 kV. And I already discussed that X double dash indicates the subtransient reactance of the entire power system. So the subtransient reactance of the generator 1 is given by 0.655, and the subtransient reactance of generator 2 is 1.31 ohm. See, this is for example. I'm not going to say you need to consider the same example. So you will have so many types of connection. I mean, so many single line diagrams are available. So in order to explain the concept of the per unit or the single line diagram, I have taken this example, but I am not going to restrict you to consider the same, right? So this is example. So in suppose if you are getting the same question in your university question paper, you need to consider your own example and you need to explain that diagram what you have taken, right? Now the section 2 contains, so see here, so this is LV means low voltage side. So transformer T1, you will have 2 transformers, transformer T1 and transformer T2 in section 2 and section 4, and you will also have section 3, that is the transmission lines. So just now I told you that the equivalent circuit or the standard symbol for representing the transmission line is a straight line. So here this straight line indicates that it is a transmission line which is having a resistance of 17.4. You see, you don't have the total length of the transmission line. You don't have the total length of, sometimes I'm also going to mention that the total transmission line length is equal to 10 kilometers. So what is the total resistance value? This is 17.4 ohms per kilometer. If I have given you like this, now for total 10 kilometers, 10 multiplied by 17.4, so that is the total impedance have been connected in the transmission line, and you need to consider the same. Okay, so in this case, the transformer primary winding and the transformer T1, transformer primary winding and secondary winding both have been connected in a star connection, and the neutral is grounded. And similarly, the primary winding of transformer T2 is star grounded, and you need to remember, later I will tell you one important point regarding the transformers. Now this is the secondary of the transformer T2, that is a delta connected. So now the section 5 contains, suppose he, in this particular case, he has not mentioned anything regarding whether this is a motor or generator, but if he has not given, means obviously we need to consider our, we need to consider our way. So I'm saying that you can consider this as a generator. So generator 3 is also connected at the section 5, and the rating of generator 3 is already given 300 MVA and 3.81 kV. X double dash is equal to 0.145. So you will have the static loads which have been connected at this point. So that is 300 megawatts, 3.81 kV and zero point 0.9 lagging power factor load have been connected at this one. And the very important point you need to remember throughout this chapter is, just wait a moment, I will tell you what is that important point. So if you are connecting two transformers in series, you are going to connect the two transformers in series. That means, now consider this one, consider transformer T1, consider transformer T2. Now these secondary of the transformer 1 have been connected to primary of transformer 2. In this particular case, the secondary voltage of T1 is equal to the primary voltage of the T2. That is very, very important. If you miss this point, obviously your problem will be incorrect. Your problem will not be evaluated, right? So that is a very important point you must remember. Always the secondary of the first transformer voltage, I mean secondary voltage of the first transformer is equal to the primary voltage of the secondary transformer. Why? Because these two have been connected in series, right? So you must remember this point throughout this subject, right? Next. So latter per unit quantities. Now, as till now we have discussed about the single line diagram or one line diagram of a power system. Now we are going to discuss about the per unit quantity. What is a per unit quantity and how it is used, and where we are using this type of per unit quantities, right? Now see here, the first point is various section components of a power system may operate with different voltages and power levels. Earlier we have seen one example, one simple example. So in that example, we are using three generators. So three generators are having different ratings, different power ratings, or different voltage ratings. Similarly, we have used two transformers. Two transformers are also having different specifications. Okay, so no transformer or no generator will having the same capacity. Most of the times, different capacities and different voltage levels, different power levels are available. So if that is the case, in order to make the analysis simple, we are going to express the specified parameters. That means voltages, powers, current with respect to a common base value. Okay, so to understand the concept of per unit quantity in a simple way, I have taken a simple example of determining or finding the distance between 2 points. First point is, point number 1 is Eluru, and point number 2 is Vijayawada. So in order to, what is the difference? So suppose if I ask the same question to X, I mean some person X, tell me the distance between Vijayawada and Eluru. maybe some X gives some answer, Y gives another answer, Z gives another answer. But as far as the individual person is concerned, all the three answers are correct. Why? Because in Eluru, I have not given any reference value. If I have given you the reference value, obviously the three and X, Y, Z answers are equal. If I have not given the reference values, how can you say that this is correct or this is wrong? Okay, so if I mention what is the distance between Sir C.R. Reddy College of Engineering and the bus stand, Pandit Nehru bus stand in Vijayawada. So you can say that, sir, it is 60 kilometers. So suppose if I have not mentioned this CRT source point, that is CRT College of Engineering, how can you measure the distance? So from Otluru to that bus station, the distance is different, and the distance has been increased when we go beyond the Otluru. That means Satrambadu, Shantinagaro, RR etc., etc. So likewise, we can understand, easily understand. So that's why if I have given you the reference point, the analysis becomes very simple. So likewise, in this particular case also, different equipments or different components are having different specifications. It is not possible to analyze that system behavior. So in order to analyze or in order to make the analysis simple, we can use the base value. So all the values or all the components have been brought to the some base or the reference value. The base or reference value. Okay. Now see how I am defining the per unit value of a power system. So per unit value is equal to the actual value by the base value. So this is a very, very important formula you have to remember while doing the problems. So how can we define the per unit value? So per unit value of that system is equal to actual value by base value. But always the per unit values are represented, are expressed in terms of percentages. So how can we express the per unit value in terms of percentages? Just you multiply the actual value by base value with the 100. So you can get the percentage of per unit value. So this is the formula. Okay, please make a note. Per unit, how can we define the per unit value? So per unit value is defined as the ratio of actual value by base value. So per unit values are always expressed in terms of percentages. So percentage of per unit is equal to actual value by base value multiplied by 100. Okay. Now let us move on to the next one. See, subject is very simple. The only thing is you need to focus or you need to concentrate. Whenever you are having some doubts, you please note down those doubts at one place. After the end of the session, I will give you some additional time for clarifying your doubts. Okay. So whenever you are having some doubt, you please raise your hand so that I will give you control for unmuting yourself. Okay. Next. Now, expression for per unit value. So how can we determine the per unit values in a power system? So per unit value maybe it is an impedance or it is a current or it is a voltage. Okay. So expression for per unit value. So in this particular concept, I have taken, whenever I use the word let means, that is my assumption. I have assumed that the base KVA, so KVA base, so K, now see here. So this is KVA base. This is the base value, the power. So KVA is nothing but power. Please remember, this is the unit of power. The power rating is nothing but KVA base. This is the base value. So KV base is the base voltage in KV. These are my assumptions. I base current in amperes. These are not the actual values. In order to determine the per unit values, actual values have been mentioned in the problem itself, but you need to consider the base values. So once if you obtain the base value, obviously you can define the, or you can determine the ratio between the actual value and the base value. You can get the per unit value. So likewise, so in this particular case, I have taken KVA base as the base KVA. KV base is the base voltage in KV. I base is the base current, and ZBA is the base impedance in ohms. Okay. We already know that the voltage is measured in terms of kV. How can we determine AB, IB? So IB is equal to, if I multiply IB with the KV base, now what you will get? Voltage multiplied by current. You will get the power. Now see here, our P is equal to V into I. Okay, but in this particular case, the power is nothing but base power. What is the base power? Base power is always expressed in terms of MVA or KVA. Either you need to consider MVA base or you need to consider KV base also. Okay, so power is equal to voltage multiplied by current. So if I want to measure IB, now take a difference between, I mean take a ratio between KVA base divided by KV base. So make this as equation number 1, right? Now see, next one is jet base. So how can we obtain jet base? Nothing but V base by I base. VB by IB. B is equal to I into jet. So similarly, jet B is equal to VB by IB. But already we know that VB is equal to, already we know that VB is equal to, is expressed in terms of KV. So in order to compensate that, we are going to have 1000 in the denominator of that equation number 2. Now see this. Now see this. This is equation number 2. So simply all we know all the equations. So we already know that V is equal to I z, power P is equal to V into I. The only thing is here we are going to have the base values. We need to represent this with the base values. That is the only difference between this one and that, right? So by substituting equation 1 in equation 2, what is equation number 1? So we know that equation number 1 is equal to IB is equal to KV base by KVA base by KV base. So now see here ZB is equal to KV base. Numerator term is as it is. So in the denominator, in place of IB, you are going to substitute that KVA base by KV base. Now you take this denominator to the numerator. Obviously, this may leads to KV base whole square by KVA base. So when you multiply KVA base with 1000, this will become MVA base. So finally, Z base is equal to KV base whole square divided by MVA base. This is a very important formula. If you forget this formula, then nobody is trying to help you to determine the per unit values in the chapter number 1. Chapter number 1 is very easy, very easy. Once if you remember all the formulae, if you forget about the formulae, then nobody is trying to help you, right? So ZBS is equal to KVA base whole square divided by MVA base. Please try to write down somewhere else. Okay. Now, suppose if I want to measure the per unit impedance value, okay, just now I have discussed about the per unit value. So per unit value of power, per unit value of voltage, per unit value of current, or per unit value. So most of the times we are talking about the per unit impedance. Per unit impedance. So how can we define the per unit impedance? So per unit impedance is equal to actual impedance in ohms divided by base impedance in ohms. So actual impedance, directly he has mentioned that actual impedance in the problem itself. What about the base impedance? Then in order to determine the base impedance, you must have the information regarding KV base of that component and MVA base of that component. Suppose if we want to determine the base impedance of a transformer or a generator or a transmission lines, definitely the specifications have been mentioned in the problem itself. Okay, so from that you have to consider the actual impedance and you are going to obtain base impedance. Once if you know these two impedances, that value, see here, that value is nothing but per unit impedance. So per unit, so please make a note, they put this in a square box. Z per unit is equal to Z actual by Z base. Now only we have derived the expression for Z base, KV base square divided by MVA base. Similarly, I have substituted the same in this case. So now if I simplify this, obviously what you will get? So Z per unit is equal to Z actual multiplied by MVA base. This is a very important formula. Please make a note. MVA base divided by KV base square. Whenever I say this is important, means you need to focus more. and you need to make a note on that particular point, right? So Z per unit is equal to this is this. Z actual multiplied by MVA base divided by KV base whole square. Okay. So this is about the expression for determining the per unit value of the system, right? Okay. Now, anyone is having any doubt? If you are having any doubts regarding this, you please raise your hand so that I will give you control to unmute yourself. Now today we have discussed about the single line diagram, and we have discussed about the definition of per unit value, and we have derived the expression of determining per unit impedance of a power system. Okay. I think no one is having any doubts regarding this. So that's all for today, and remaining we will continue it in the next class, right?